In this video, we're going to be talking about rotation. So how do we rotate a point or an entire figure about a fixed point? And that fixed point is going to be called the center of rotation. So it's going to spin around that single location. In our class, we're going to be talking about three main types of rotations. We can rotate 90 degrees in a counterclockwise direction, or we can rotate 90 degrees in a clockwise direction, or lastly, we could rotate 180 degrees. So it doesn't matter what direction we go in. When we do that, we'll end up at the same spot in either direction. There are some coordinate rules, some patterns we can use and apply to our coordinates in order to rotate them. We'll come back to these rules when we start to visualize some things later on in the video. But for now, I just want to focus on, can we identify these rotations? And then we'll get into how we can use these coordinate patterns to also help us identify a rotation. So here we have our first example here. We have triangle GFH, and it is getting rotated over to here. I know it's a little light, but you have apostrophes on these coordinates here. So that would be our transformed triangle. So we're coming from here over to here. Actually, two different ways that we can interpret this. We could just simply go 90 degrees counterclockwise, and we would end up at that spot. But hopefully you can also imagine that if we go 270 degrees the opposite direction, we would end up at the same spot. If we go 360 degrees, we would end up at the same spot. So if we back up 90 degrees, then we would have gone 270 degrees. So sometimes we'll be able to use that interval of 270 in a sneaky way. We'll see that a little bit later on in the video as well. Certainly okay in this case to just say it's 90 degrees counterclockwise. So some other things that we can actually interpret from this diagram here. Let's try and look at the coordinates of our F points. So our original F is at -4, -2, and it got rotated to the coordinate 2, -4. So hopefully you can see that our coordinates got flipped, and then the left value after we flipped was the opposite value of what it started as. So rather than -4, -2, we had -2, -4, and we make the left value the opposite. That's that pattern that we see up here describing a 90-degree counterclockwise rotation. We can flip our X and Y coordinates from their original spots, and then we can make the left value the opposite. And when I was learning this, I think this directional arrow helped me keep these two straight because they're very similar rules, and I used to mix them up. If you actually just draw an arrow that's going counterclockwise, it will remind you which of these two to make the opposite. So you could play around with these other coordinates. You can compare H to H prime or G to G prime, and you would see that pattern happening, that their coordinates are flipped and the left value is the opposite. Another thing we can also take a look at here is the relationship from our original coordinate to that point of rotation at the origin, and then back to our transformed rotated point. If we connect our original point to our point of rotation, almost like making the hands of a clock there, it's going to be spinning now this direction 90 degrees. And if we actually connect the origin to our new point, we'll see that actual angle of 90 degrees occurring between those two segments that we drew. It's also true that the distance from your point to your point of rotation should be equal to the same distance from your rotated point back to your point of rotation. So again, much like the hands of a clock, when your clock hands are spinning around the clock, they're not growing or shrinking, they're not changing size. And so in the same way, we want to make sure that the same thing happens when we do our rotations on a coordinate plane. We'll talk about this one more time when we practice using a protractor. If you have one, you can follow along. Otherwise, just listen to what I'm describing and imagine using a protractor while you do it. Let's take a look at one more example here, just interpreting a rotation. So here we see another triangle ABC. rotated in some fashion over to this ABC prime triangle. Maybe you already knew that that looks like it's a 180-degree rotation. But again, one way that we can prove it is by looking at our coordinates. For example, if we look at the coordinate C, that's at 3, 1, and C prime is at -3, -1. So comparing our coordinates, we see that we have the exact same coordinates except that our rotated coordinates are the opposite of what we started with. And so if we go back up here, we can see that that is indeed the rule for rotating 180 degrees. Just make your coordinates the opposite of what they started as. Don't make this common mistake of flipping your coordinates because we end up flipping them for our 90-degree rotations. Don't flip them for 180 degree. Keep them in the same spot and just make them the opposites. And then lastly, since we didn't talk about it yet, 90 degrees clockwise, that rule, we're going to do the exact same thing we did up here. Flip our coordinates, but this time we're going clockwise or spinning to the right. So I'll remember that if I draw my arrow spinning to the right, I'll make the right value the opposite after I flip my coordinates. So we're going to practice using these rules in the next section. This time we're going to practice performing a rotation. We're going to plot some points here, RU and N, and connect them to draw a triangle RUN. And then we're going to rotate about the origin 3 different ways here. So for part A, we're going to rotate 90 degrees. That's a positive angle measure. Positive angle measures are going counterclockwise, spinning to the left. So let's take point R. We could connect it to the origin, and we could take a protractor, lay it on that segment, and draw 90 degrees from there. And then measure that segment. And over here on this ray of our 90-degree angle, we can measure the exact same length of a segment, and the end point that we get to would be our new R location. But rather than using protractors, we can use our coordinate rules. So if we're going 90 degrees counterclockwise, we're going to flip our coordinates and we're going to make the left value the opposite. So taking 4, 2, we'll say is 2, 4, and then we'll make the left value the opposite, so -2, 4. So there's our new R rotated 90 degrees counterclockwise. Doing the same thing to the next 2 points. Taking U and flipping our coordinates, instead of 4, 6, we're going to say 6, 4, and make the left value the opposite, so -6, 4 instead, and plot that point as our rotated U point. Lastly, we'll take N at 7, 6, we'll flip our coordinates and say 6, 7, and we'll make the left value the opposite. So now we have -6, 7. We can plot our N transformed and connect our points to draw our newly transformed triangle. And then we can visualize and see that it did in fact rotate 90 degrees. If we connect all of our points to the origin back to their corresponding points, you should see right angles occurring there. All right, we're going to do it again, but this time we're going to rotate our original triangle, and we're going to rotate it -90 degrees, which is another way of saying clockwise. This negative symbol has nothing to do with the measure of the angle, it has everything to do with the direction of the angle. So positive angles go counterclockwise, and negative angles go clockwise. So similar to what we just did, except we're going to make the right value the opposite after we swap. So we're going to take our original R coordinates, flip them so it's 2, 4, and then make the right value the opposite. So now it's 2, -4. Plot that. Take our coordinates at U, swap our coordinates. Instead of 4, 6, we'll say 6, 4, and then we'll make the right value the opposite. So 6, -4 is where we'll put our new U. And then lastly, N was at 7, 6. We'll flip our coordinates, say 6, 7, and make the right value the opposite. So now we have 6, -7. Plot that, connect our points for our triangle again, and then we can see how R was rotated 90 degrees this time, clockwise. If we connect U back to the origin, we can see that 90 degrees, and then finally N, connect your ends back to the origin, you'll see that 90 degrees. Lastly, let's do a 180 degree rotation, starting back again with our original triangle. So taking R, which was at 4, 2, and not swapping them, but just making them the opposite, gives us -4, -2. So plot our R there. Then we got U, which was at 4, 6, and we'll make each of them the opposite, don't swap. So -4, -6. Plot that. And then lastly, N was at 7, 6. Again, don't swap, just make them the opposites. So -7, -6. So connect those points, draw your triangle, and now we got our third rotated triangle. This time it's 180 degrees. And when you connect them back to the origin, you just have this straight line, and we know that a straight line measures 180 degrees. All right, I gave you another example, which is pretty much practicing the exact same thing, just with a different starting triangle. So go ahead and take a moment to practice that one on your own, and then you can pause the video and check your answers by looking at it here. All right, hopefully you came about with the same answers. Last question here, does rotating a figure change the shape or the size of our triangle? Hopefully you can see through the examples that we've done that no, it's not going to change the shape or the size, so rotating is going to keep figures congruent. All right, a couple more challenge questions here at the end. How could we rotate 270 degrees about the origin? So we hinted at it at the beginning of the video. We can actually do it a few different ways. We could take our coordinates here and we could just rotate them in intervals of 90 degrees. We could go 90 degrees counterclockwise once. We could go 90 counterclockwise again twice. And then for a third time, transform those coordinates 90 degrees counterclockwise one more time to get to 270 total degrees. That would probably be the least efficient way to do it, but it works. You could definitely do it that way. We could also maybe cheat a little bit, do it in 2 steps. We could rotate 180 degrees counterclockwise, come over here, and then rotate one more 90 degree counterclockwise rotation to get up to 270. That would also work. But there is actually a 1-step process to doing this. Remember how we said that if we rotate 360 degrees and just back up 90 degrees, we will have ended up at 270 degrees. So actually, all we need to do is rotate 90 degrees in the opposite direction to end up in the same spot as rotating 270 degrees. So rather than doing 270 degrees counterclockwise, we can just do 90 degrees clockwise and we'll end up in the same spot. So using our pattern, taking our coordinates, for example, R is at 3, 3. Let's flip our coordinates and make the right value, since we're spinning to the right clockwise, make the right value the opposite. So 3, -3 will be our new R spot. S is at 4, 1. If we flip them and make the right value the opposite, we got 1, -4. So there's our new S. And then finally for T, which is at 2, -2, we could flip our coordinates and make the right value the opposite and end up with -2, -2, which is our new T spot. And again, we can check our work. Go back to the origin from each of your T's. You should see a 90-degree angle occurring. Same thing with R, and the same thing with S. It's kind of a neat cheat there. Rather than having to do 270 degrees in intervals of 90 or 180, we can just go the opposite direction and solve the problem in 1 step. All right, lastly, how do we rotate if there are other intervals other than 90 degrees? For example, we want to rotate 80 degrees. And this time we can rotate about any point. We don't have to rotate about the origin. So for example, we're going to rotate from our point A at 3, -2. So there's going to be our anchor point or our center of rotation. Let's plot these 3 points and draw a triangle TOY. If you have a protractor, you can go ahead and practice this, or just listen to my description and imagine how you could use a protractor here. Let's start with O. We're going to go from O and we're going to connect it to our point of rotation, again making the arm of a clock almost. That's what's going to be rotating and spinning over to the other side. 80 degrees, this is positive, so we're going counterclockwise. Once we have this segment drawn, that'll be the bottom of your angle. So you could line up your protractor with the center at your point of rotation and in line with the segment, and then measure an opening of 80 degrees and put a little point out there. Next, we got to make sure that this segment right here is congruent with its segment on the other side after the rotation. So let's measure this segment length from our point of rotation to O. And then over here with this ray that we drew for our angle, we just have to measure a congruent length and then cut it off right there, and that end point is the new location of your rotated point. This is kind of approximated. It's not a very super accurate way of doing it. We got a lot of room for error there, but we're getting close. We're going to do the exact same 3 steps again. This time let's do it with T. We'll connect T back to our point of rotation. We'll use that as the bottom base of our angle to measure 80 degrees away from there. Measure that segment length and create a segment length that's equal over here along that other ray of your angle. Cut it off at the same length, and that is the endpoint for the new T that was rotated. And then lastly, one more time, we're going to do the same thing with Y. Connect Y to your point of rotation. That's the bottom of your angle. Line up your protractor on that. Measure 80-degree opening from there, opening counterclockwise. Measure that length from your point of rotation to Y and create a segment that has an equal length over here on your other ray. Cut it off right there at the end of that segment, and that's your new Y point. Now we can connect our points, and we got our triangle that was rotated 80 degrees counterclockwise. All right, so a bit of a challenge there at the end. Certainly, if that's too much for you, don't focus on that. Certainly be able to rotate 90 degrees, both clockwise and counterclockwise, and also rotate 180 degrees, and then be able to think about special instances of intervals of 90, like can you rotate 270 using a variety of different tricks. Good luck rotating points. Practice those 3 main rotations and know these coordinate rules.